Okay, a lot of people really struggled on this week's quiz, so I went ahead and made a video so that we could go over it together. Okay, so we have this family of linear systems, and I asked you to draw the corresponding curve in the trace determinant plane. Now, here's the trace determinant plane. I've marked in purple the t-axis, the positive d-axis, and this parabola. These are my critical loci. That's where the type of phase portrait I have changes. Okay. All right, so if I look at this, I can see my trace is the square root of a, because it's just the square root of a plus 0, and the determinant is 0 minus -1, so the determinant is 1. Now, a lot of people saw that, and they said, oh, so d is 1, and they just drew a line at height 1. They were ignoring the fact that there are some restrictions here on t. Okay. Now, I know we've sometimes been working in the complex numbers, but we are not doing that here. Okay. I know we're not doing that if we're talking about the trace determinant plane, because I'm putting the trace on a number line. If I'm putting numbers on a number line, there's space for 0, there's space for negatives, and there's space for positives. There's no place to put anything imaginary. Okay. And I've got another number line for the determinant, so the determinant can be 0, positive, or negative, but it can't be imaginary either. Okay. So we have sometimes been working with imaginary numbers. We have never had an imaginary number as part of our matrix. We've been looking at real systems, and sometimes we'll complexify the problem a little bit, or we'll allow ourselves to have complex eigenvalues or eigenvectors in order to do a little bit of work in the complex numbers in order to go back and get our real solution. But we've always really been working primarily in the real numbers, and the complex numbers have just been a tool to get solutions to our real differential equations. Okay, so we're working in the real numbers, so a has to be bigger than or equal to 0, and t is the square root of a, so t has to be bigger than or equal to 0. Now, some of you tried to say, well, aren't there 2 square roots of any positive number? Like, doesn't 4 have 2 square roots, 2 and -2? The answer to that is yes. If x squared is equal to 4, there are 2 solutions, and they are the 2 square roots of 4, 2 and -2. However, if x is equal to the square root of 4, there is 1 solution, because that is the principal square root. This symbol does not mean anything I square to get 4. It means the non-negative thing I square to get 4. So that symbol means principal square root. And there's only one of those. And if you think about it, if I had asked you to graph y equals the square root of x, without even thinking, you guys would draw that. You wouldn't draw in a second negative branch to say, oh, but there are 2 answers, because you know the square root is a function. And if it's a function, each input has to have a unique output. Okay. So what I have is d equals 1, but t has to be bigger than or equal to 0. So I'm not getting a full line, I'm getting a half line, just the right half of the line d equals 1. Okay, so then we wanted to take a look at what sorts of phase portraits could we get. And there are really 4 different types of phase portraits that we could get, because right here, I'm going to just label that point B. Right here, I'm at a critical locus. Okay. Then on this interval, I'm in the same basic region. So I'll just draw a representative point there. Here, I'm in the region that's above the parabola, but to the right of the d-axis. Here, I'll call this little d. That's on the parabola, so that's a critical locus. Okay. And then we'll call this point over here E. That's in this region where we're below the parabola, but we're above the t-axis. Okay. Now, for the regions, so C and E are in regions between critical loci. For that, I just asked you to draw a general phase portrait. So let's do that first. Let's take a look at C. Okay. And if I remember what I get, great. If not, I can always work it out, because I know the characteristic equation is lambda squared minus t lambda plus d equals 0. Now what that means is that lambda will be t plus or minus the square root of t squared minus 4d all over 2. So that reminds me that the equation for this parabola is t squared minus 4d, because the parabola is where this thing is equal to 0, and that's the boundary between where this thing is negative and where this thing is positive. Where it's negative, I'm getting complex eigenvalues. Where it's positive, I'm getting real eigenvalues. Okay, so if I look at C in here, I can sort of see this would be where t is 0, and then we're moving across. Let's actually figure out what t is at point D. Because that would be where t squared minus 4d equals 0. But I know d is equal to 1. So t squared would equal 4. And I can see t here is positive. So t is the positive square root of 4, which is 2. Okay. So in here, t might be something like 1. Notice 1 minus 4, that's going to give me something negative. So I'm going to have complex eigenvalues. But if I take a look, the real part is just going to be t over 2, which is going to be positive. Okay. So if I have complex eigenvalues with a positive real part, that's going to give me that my equilibrium solution at the origin is a spiral source. Okay, now if I take a look at part E. Okay. Now here we've passed 2, so t is bigger than 2, so t squared minus 4d is going to be positive. That means I'm going to have 2 positive real eigenvalues. Okay, because t squared minus 4d is going to be smaller than t squared, so this square root will be smaller than t, so whether I add or subtract it, I still have something positive. So at E, I'm going to have 2 positive eigenvalues, so I'll have 2 straight line solutions that are going away, and one of them will dominate as we go off towards infinity. So I would just have a plain old regular source. Okay. Now, the other points, B and D, those are places where we're actually on a critical locus. And so there, I can actually get the exact value. We've already done it, actually, the exact value of t. I can get the exact value of A that puts me there. So I can get the specific matrix and draw a much more accurate phase portrait than just sort of a generic one. So if I'm at part B, where we said t was equal to 0, and that's going to mean that A is equal to 0. So my matrix here is 0, 1, negative 1, 0. So my characteristic equation is lambda squared. My trace is 0. The determinant is still plus 1, so that equals 0. So lambda squared equals negative 1. Lambda is plus or minus I. So that makes sense. We're inside of the parabola, which is where we said we were going to have complex eigenvalues. On the positive d-axis, we actually have purely imaginary ones. And remember, when we have purely imaginary eigenvalues, what that means is we're getting a center. But if I have a center, I want to know, am I rotating around that clockwise or counterclockwise? And that's where I can use this matrix. What I'm going to do here, actually I'll do it over here, is I'm going to just pick the point 1, 0. So I'm going to take my matrix 0, 1, negative 1, 0. I'm going to multiply by 1, 0. Trick is that gives me 0, negative 1. That just gives me my first column. So that tells me that when I pass through this point, I've got to be going down. I've got to have a vertical tangent. Well, if I'm here and my tangent is going down, that's enough to tell me that we're going clockwise. A lot of folks forgot that when you do have spiraling behavior, you need to pick a point, multiply by your matrix to get the derivative at that point, and that gives you the direction of the rotation. Okay, so let's take a look now at point D. So at point D, we had determined that t was equal to 2. That's going to mean A is equal to 4. Okay. So my matrix is the square root of 4, which is 2, 1, negative 1, 0. My characteristic equation is lambda squared. My trace is 2, so minus 2 lambda plus 1 is equal to 0. That factors. Lambda minus 1 squared equals 0. So lambda is equal to 1. So we have one repeated eigenvalue. And that's what's going to happen if we're actually on the parabola, that we get a repeated eigenvalue. So now I need to see, do I have one or two independent eigenvectors? So if I call this matrix A, I'm going to take a look at A minus my eigenvalue 1, so A minus 1i, times the vector v1, v2. I want that to be 0, 0, and I'm looking for a non-zero vector that makes this true. So A minus I would be 1, 1, negative 1, negative 1, v1, v2 equals 0, 0. So the corresponding system here, let's see, I'll give myself some space over here. Corresponding system is v1 plus v2 equals 0, negative v1 minus v2 equals 0. That's a dependent system. This equation is just a multiple of that. If you don't get a dependent system, you have made a mistake. Either what you think is an eigenvalue isn't an eigenvalue, or you calculated your matrix wrong somehow. Now, when we're working with complex numbers, it's not always obvious that you get a dependent system. So when we're working with complex numbers, I'll look at it and say, well, it's not obvious, but I know it should be dependent because I know I have an eigenvalue. But with real numbers, it should be obvious that one equation is a multiple of the other. So I can solve this system, but there are infinitely many solutions. This just means v1 has to be the opposite of v2. So I'm going to take as my eigenvector 1, negative 1. So that gives me my straight line solutions. So I'm going to have my equilibrium solution at the origin. I'm going to have straight line solutions on the line determined by 1, negative 1, or y equals negative x, or x equals negative y, however you want to think of that. And remember, when we only have one independent eigenvector, what we have is wannabe rotation, wannabe spiraling. The solutions are going to want to spiral, but they can't because they're not allowed to cross this line. So just like with the center, I need to see what direction are they trying to spiral in. So I'm going to do the same thing I did there. I'm going to pick a point. I usually just pick 1, 0. Okay. And I'm going to take my matrix. So the matrix here was 2, 1, negative 1, 0. I'm going to multiply by 1, 0. And that's going to give me 2, negative 1. So at this point, we're going over 2, down 1. We're rotating this way. So that's wanting to spiral clockwise. Okay, because we're coming down as we cross through the x-axis. So I'm going to now draw wannabe spiraling going in a clockwise direction. But again, if you have a center, or if you have a spiral source, or a spiral sink, or a wannabe spiral, you've got to check the direction of rotation. Now, because for C, where we had a spiral source, I just asked for a generic graph. There, I hadn't asked you to find the specific matrix, so you didn't need to check. But if you have a specific matrix and you're actually drawing the phase portrait for that specific linear system, that's something that you need to check. Let's make sure I remember to classify. This would be a source. I think I said the last one, the one here was a center. If I forgot to write that down, I've at least said it. So this was a center. This was a spiral source. This was a source that wanted to spiral but couldn't. And this was a source that didn't even want to spiral. We had two straight line solutions for this one.